Ma'am, let's start, ma'am. Ma'am, let's start the session, ma'am. Ma'am, let's start the session. Amuda, ma'am, can you able to hear me voice, ma'am? Ma'am, your voice is not able to hear, ma'am.
I'm now only connected.
Okay,
Okay.
ma'am. Okay, ma'am. Now clear, ma'am.
Yeah.
Okay, ma'am. Let's start the session, ma'am.
Yes. Proceed.
Okay, ma'am. Very good morning, participants. I would like to welcome all the participants for day 3 session 1 of AICTE sponsored 2 weeks online faculty development program on emerging trends and challenges in a VLSI mixed signal processing for a fourth industrial revolution. Welcome you all. It's my immense pleasure to welcome our today's resource person, Dr. V. Amuda, professor at Savita University, Chennai, for this session. Welcome you, ma'am.
Welcome, Pa. Thank you.
When your actions inspire others to dream more, learn more, do more, become more, you are a leader. Let me give the short intro about our resource person, Dr. B. Amuda. She completed her BE in Electronics and Communication Engineering from Alagappa Chettiyan College of Engineering and Technology at 1994 and completed her ME in Communication System from National Institute of Technology, Tiruchirappalli at 2000 and completed her PhD degree in SOPC Places Speech Recognition System from National Institute of Technology, Trichy at 2009. Her main research interests are convolutional neural network, signal processing, cognitive radio network, and VLSI based system design. She has 2 years of industry experiences and more than 23 years of experiences in teaching at various reputed institutions. Presently, she is working as a professor at Savita University, Chennai. She has published more than 30 papers in international journals and presented more than 15 papers in national and international conferences. She did the various funded projects and also she acted as the PhD supervisor under Anna University and St. Peter's University. She also got a patent for smart remote garbage monitoring system. She acted as the chairperson and delivered special lectures in various national and international conferences, workshops, seminars, and training programs. Her professional bodies are like IST, IET, and IEEE. Now I'd like to hand over the session to our resource person, Dr. V. Amuda. Please, ma'am.
Thank you for the nice introduction. May I know your name, Pa?
No, Bhaskar, ma'am.
Bhaskar, thank you.
Yes, ma'am.
Shall I share my screen?
Yes, ma'am. You can share now, ma'am.
How to go to my menu?
Ma'am, at bottom you
Yes,
can see
yes,
the
yes,
share
yes.
screen option.
Good morning, one and all. I am Dr. V. Amuda, Professor, Department of Electronics and Communication Engineering, Savitha School of Engineering, Chennai. Actually, there is a close relationship between Kongunadu College of Engineering and my native place. My native place is located nearby Kongunadu College of Engineering in it's called Anikalpatti. My father is a retired school teacher. I'm happy to be here with the presentation that I completed my BE in 1994, not like the situation here in 2020. That time, I am the only female candidate from my community who passed the BE degree and got the PhD degree. Studying is one part of the life, but that is not the whole part of the life. We have to concentrate on social activities like helping others, sharing thoughts in technical and non-technical things. Today, I'm happy to be invited by my son, Mr. T. Dinesh Kumar, Assistant Professor, EC Department. He is my son, and I'm happy to be here with his presentation. The topic is significance and development of system on programmable chip-based applications.
Ma'am, whether you can share your screen, ma'am?
It is shared, Pa.
No, ma'am. We can't able to see your screen, ma'am.
1 minute. You are not able to view?
No, ma'am.
This screen you are viewing?
No, ma'am. There is no screen sharing from your side, ma'am.
Share screen தானே பா போகணும்.
Yes, ma'am. Share screen, ma'am.
Green கலர்ல இருக்குல்ல அதானே.
Yes, ma'am.
Now you are viewing.
No, ma'am. அதுல போயிட்டு லைக் செலக்ட் பண்ணிருங்க மேம் எந்த ஸ்கிரீன் ஷேர் பண்ணணும்னு.
இப்ப பாக்குறீங்களா?
நோ மேம்.
மேம் ஷம்லா மேம் share screen now is it viewing? Bhaskar?
No, ma'am. There is a no screen sharing from your side, ma'am.
இல்லை என்னோடது இங்கே டெஸ்க்டாப்ல இருக்கு. இதுதான் இல்ல இது வாட்ஸ்அப் இது இந்த ஜூம் 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 இங்க இங்க ஷேர் ஸ்கிரீன் போட்டாதான் இதுவே வரலைங்கிறாங்களா. உங்களோட ஸ்கிரீன் எது? நானும் ஓப்பன் இங்கே டெஸ்க்டாப் போயிடுறேன். இங்கே வச்சுக்கணுமா? எந்த விண்டோ உங்களோட மல்டிப்ளை ஓப்பன் பண்ணிருக்கீங்க? இதுதானே.
அதுக்கு மேல ஏதாவது இதெல்லாம் தெரியுங்களா உங்களுக்கு? இதானே
வேணாம்.
போறேன் மேல. காஃபி வேணாம்.
இல்ல மேம், அதுதான் மேம், அதான் மேம் ஸ்க்ரீனு.
இதானே ஸ்கிரீனு.
இது ஸ்க்ரீன் கிடையாது. இது
இல்ல எங்க
ரெஜிஸ்ட்ரேஷன்.
உங்களோட இது அந்த இது பிரசன்டேஷன்
இங்க இருக்கு. பிபிடி.
அது இருக்கட்டும்.
ம்.
இது
இதான் இதான் இதான்.
Yes, ma'am. Now visible, ma'am.
Now are you able to you?
Yes, ma'am. Visible, ma'am.
Okay, okay. Thank you.
Okay, ma'am.
The content of the today's topic is scaling of digital integrated circuits, different platform for implementation, review of MP, microprocessor based and DSP processor based implementation, parallel processing, pipelining. What is the difference between parallel processing and pipelining? FPGA versus ASIC, SoC, system on programmable chip, hardware software co-design, speech recognition system as SOPC, and conclusions. When you look into the scaling of digital integrated circuits, as you all know, the small scale integration is actually having number of gates less than 10. Examples of ICs in the SSI is logic gates and flip flops, and the medium scale integration is up to 1000 gates. Examples of ICs of 1000 gates is counters, multipliers, and adders. Large scale integration is about up to 10,000 gates. Examples of LSI is 8-bit microprocessor, ROM, and RAM. And in the 1980s and 90s, VLSI came into picture with more than 1 lakh gates, that is 32-bit microprocessors and peripherals. In 2000, we came with ultra large scale integration where more than 1 lakh gates are there with high K dielectric materials. Why this high K dielectric materials is coming to picture is to avoid the mass leakage. Actually, the process name 856 is introduced in the year 1997, and 858 is introduced in the year 1999. PX60 is in the 2001, with the process generation is called as 0.13 micrometer. P1262 is in the 90 nanometer technology with the polysilicon. P1264 is in the 2005 with 65 nanometer technology with polysilicon. P126 1266 is coming in the year 2007 with the high K and metal gate electrode. P1268 is in the year 2009 with the metal with the gate electrode with high K, high dielectric material. P1270 came in the year 2011 with the high K with the metal gate electrode. These are all the high K and metal electrode evolution starts from the year 2005 onwards. 2005 onwards, we are using metal electrode as a gate. Previously, it is used as a polysilicon. When you draw with a N mass, And the p-type substrate will be the p-type substrate, and n plus diffusion will be the source, and n plus diffusion will be the drain, and the gate will be a polysilicon. But now after 2005, the gate is made up of metal for the improvement of high k to avoid leakages. The scale of integration starts with the micron to nanometer. Um, Scaled transistors provide higher performance, lower power, lower cost per transistor. In the year 2020, you are come to a 10 nanometer technology, 7 nanometer technology. What is nanometer technology? The length of the channel is between the source and the drain, that is called L. Length of the channel is between the source and the drain, that is called L. L is equal to lambda, and the way lambda, the scaling factor lambda is equal to L by 2. That L by 2 is in the order of 10 nanometer, 7 nanometer, 100 nanometer, according to the technology. Okay, now we are in the era of 7 nanometer technology. In the initially, 22 nanometer technology is used for manufacturing purposes, and it is developed with the 10 nanometer technology. Now we are in the research of 7 nanometer technology. As I told, the 7 nanometer is the distance between the source and the drain. Let us look into a clear picture. What is a nanometer? The height of the human being will be 1.5 or 1.66 meter. It is in the meter ranges, and the length of the fly insect will be 7 millimeter. To visualize the nanometer technology, I am putting this picture. The might will be 300 micrometer, and our blood cell will be 7 micrometer. The virus will be 100 nanometer diameter. The silicon atom will be 0.24 nanometer. Okay, now this is the visualization of how our scaling of integration goes from meter to nanometer. The nanometer, 0.24 nanometer is the size of the silicon atom. Our research today in the VLSI field is in the range of channel length of 7 nanometer. There is a close relationship between what is our application and what is our nanometer technology. The nanometer technology is in the order of nanometer, micrometer, and things. When you go down with the channel length lesser, that is what is a channel length? As I already told, channel length is nothing but the distance between the source and the drain. So when the distance between the source and the drain, non-ideal effects will happen. The main application of that is server computing for small channel length. But if you go with high speed with lower channel length, your leakage power will be higher. Look at the picture. When the server computing is with high speed of operation, the leakage power is 1x. When the mobile is always on the on circuit, the leakage power is 0.001x. You have to realize that as the length of the channel is reduced, the leakage power will be more. Tunneling will occur. Tunneling current is the, instead of going to, the electron should go from source to drain, that is called drain current. But due to the charge channel effect, sometimes the electron will go to the source to gate, that is called tunneling current. The tunneling and all should be avoided for short channel effect. Okay, the small mobile always on circuit, that is in the order of power leakage 0.001x. Wafer scale integration, it's called super chip, which is of large size, reduced packaging, reduced cost. Parallel and supercomputers are like this. Wafer scale integration, large size, reduced packaging, reduced cost, and parallel and supercomputers. What is a system on a chip? System on a single chip is design is complex and costly. Building different components on a single piece of silicon may compromise the efficiency of some elements. So it is a single piece of silicon, different components on a single piece of silicon. As you know, your FDP is on mixed signal processing. The SOC will have both analog components and digital components together on a single silicon chip. Lower manufacturing and assembly cost, reduced power budget. There are two layers, one more layers of active electronic components vertically and horizontally into a single circuit. Communication between layers uses die scaling. Power consumption is much lower, but leakage current will be higher. Use of short vertical wires reduce the overall wire length. Power consumption is much lower, consumption is much lower, but power leakage will be higher. Use of short vertical wires reduce the overall wire length. What is an IC? We look at the diagram. Why IC development led to a high technical revolution? The PCB is having many components in the circuit, capacitor, resistors, transformers, ICs, like that. All the components are replaced on a single chip, that is called IC, integrated circuit. The integrated circuits in one chip circuit replaces large amount of discrete components on the board. What is meant by discrete components? The discrete components are resistors and capacitors. Those things are replaced by a single IC, and the IC can be a flip-flop, counter, multiplier, adder, like that. Almost all traditional discrete elements like processors, memories, digital discrete logic, and analog blocks can be integrated into one piece of silicon. When you take the substrate, yeah, I think you might have studied your twin well process. In the twin well process, you'll be having a p-type substrate, and in order to form a n mass, you have to have a p-type substrate, and n plus diffusion will be the source, n plus diffusion will be the drain. Okay. And another PMOS is required to form a inverter. We know that inverter is formed by PMOS at the top connected to VDD and NMOS at the bottom connected to ground. This PMOS and NMOSs are formed on a single silicon to form the inverter IC. To have this p-type substrate, to have the n-type substrate for the PMOS, you have to you have to design a n-well process. This n-well process will be nothing but digging the p-type substrate with the n-type material. Okay, on the n-type n-well process, n-type substrate, below to that it is p-type substrate. Commonly it is a substrate, so you have to have all the components on a single silicon for an inverter. Inverter is an IC 7404, okay, and it is having a substrate, p-type substrate. The chip architecture of system on chip architecture is as mixed signal processing. Mixed signal means what? Your analog signals and digital signals on the same chip. SOC is one of the mixed signal processor. It is having digital logic called hard macro, analog blocks called hard macro, ROM and RAM, and digital logic it's called random logic. Okay, so this is all together on a chip. That is why it is called as system on a chip. SOC, system on a chip. The system on a chip is an example of mixed signal processing because it is having both digital logic and analog logic. Not only that, it is having ROM, RAM, like that. Any implementation, if you take with the hardware design of EC department, it will be involving with microprocessor and microcontroller. Otherwise, it will have with the digital signal processor. In 1999, when I am doing my ME course, I used the DSP processor TMS 320C6201. Okay, and that is the fixed point processor I used for speech recognition application. Implementation requires microprocessor and microcontroller, otherwise digital signal processors. Field programmable gate arrays like Spartan 3E or Ultra FPGAs, or Xilinx FPGAs or Flex FPGAs you can use. Application specific integrated circuits. Application specific integrated circuit is like it is like a specific application on, it will do only the specific application on a chip. My teacher used to take one class what is called a programmable gate array. Sometimes the programmable gate arrays FPGA is a subdivision of ASIC. Subdivision of ASIC. Why? Because general processors are like a ready-made shirt. General processors are like a ready-made shirt. If you go to a shop, you'll be asking for the size of the shirt. Either it is 40 size or 42 or 44 like that. But when you go to a tailor, you'll be giving the measurement for you for your size. So application specific integrated circuits are like a tailor made shirt. For a particular application only it will operate. Like a particular person only the shirt will suit. For other persons it will not suit. But in the ready made shop, 40 size will be shooting for many people. That size will be purchased by many people, but in the tailor made shirt it will be done by only for one person, and it will be suit good for only one person. Like that, application specific integrated circuits or specific ICs for a particular application. And the system on a chip is, as you put the diagram in the previous slide, digital logic, analog logic, ROM, RAM, digital, all together is called system on a chip. Let me take a small introduction about microcomputer, microprocessor and DSP process. The need of, initially we'll start with 8051, your microcontroller, and what is the need for digital signal process. Specific DSP blocks, multiple MAC units, pipelining, all are required for DSP processors, which is not available in the microprocessors. Generally, what is a basic operation in EC department? That is the signal processing operation. The basic signal processing operation is convolution. Convolution is nothing but when you apply impulse, you'll be getting a impulse response of the system. There is a block box called system. When you apply a impulse, you'll be getting a impulse response. When you apply a particular signal, what is the response with respect to that impulse response? That is called convolution. The convolution requires multiplication and addition together, MAC operation, multiply, accumulate. MAC operation. MAC unit is not available with the microprocess, but MAC unit is available with the DSP process. That is the main difference between microprocessor and DSP process. And pipelining is one of the concept employed in DSP process, which is not available in the microprocess. Multiple MAC units are there to do many multiplications and accumulation together. The signals are very computationally demanding and requires attention to numeric fidelity, high memory bandwidth requirements, streaming data, predictable data access patterns, execution time, real-time constraints. These are all the how signal processing is taking place. There are standards, algorithms, and interfaces for that. There is a comparison table between digital signal processor and microprocessor. Have you all heard about TMS 320 C54 C50? My guide, Dr. Venkat Ramani from NIT Trichy, he's a professor in EC department. He published a book before 20 years back with the DSP process with the programming. uh, that time and all we used to conduct DSP programming classes in NIT. I am one of the speaker in during that time, during my ME courses. Okay. Digital signal processors are Harvard architecture, microprocessor or von Neumann architecture. Why? What is Harvard architecture? There is a separate address bus and uh, data bus. But in the microprocessor, both are multiplexed. Address bus and data buses are shared by one bus only. Okay, and dedicated MAC blocks are there in the DSP processor, and no MAC blocks are there in the microprocessor. Address calculation requires less time. Address calculation requires less time, and the decoding of address is more requires more time in microprocessor comparatively to the DSP process. Multi-processor link is less easy. Multi-processor link is less easy. Multi-processor link is difficult. Memory access time is fast in DSP process. Memory access time is high in microprocessor. Why I am talking about all these basic things are you have to know. Now we are in the era of mixed signal processing with factory industrial revolution 4. But what is the basic behind it? How it started? It started from DSP, microprocessor like that, and now only we are into the era of mixed signal processing. The tools used for DSP or specific tool support, primitive to moderately sophisticated, and general purpose processors are primitive to very sophisticated. The DSP specific tool support good to excellent cycle accurate simulators, DSP C extensions. Many nowadays we are using Arduino and Atmega, Arduino and Raspberry Pi. All are supporting C programming, embedded C programming. Similarly, the DSP processor also supports C programming. Third party DSP support, DSP software support. What is mean by third party DSP software support? One company, for an example, in a car company like Maruti or whatever might be, uh, in a car, they will not manufacture all the things in the car. The door and the FM, AC and all will be purchased from other persons and kept in the car. The engine is might be the trademark of that company. Remaining parts are purchased from different company names. Okay, that is called third party part. Poor to excellent, limited but growing. Okay, non-DSP third-party software support is poor, few to moderate RTOS operations. Non-DSP third-party support software extensive, few to extensive RTOS options. Links with the other high-level tools. Example, MATLAB. MATLAB can be run with the DSP processor and the GUI builders. Graphical user interface can be supported by general purpose processors. Example of DSP and MP microprocessor. In the low end and the high up GPS, the ARM is the good processor, and ARM 9E, ARM 9, ARM 7. What is there inside your mobile? Which processor you know? ARM Cortex. ARM Cortex is the processor available in your cell phone. DSP processors are C24X, C54X, C28X, C55X. All are DSP processors. The FLAC-FIN technology, C2X, C64X or there, C74X also there. ARM11, PowerPC, P4 are the general purpose processors available in the market. Okay, what is mean by parallel processing and what is mean by pipelining processing? Pipelining is one of the keyword used in digital signal process. Parallel processing means, suppose you have a process called A1, A2, A3 and A4. And another process called B1, B2, B3, B4. C1, C2, C3, C4, D1, D2, D3, D4. All the process, if they are running in parallel, then you need, suppose A1 is a multiplier, B1 is a multiplier, C1 is a multiplier, D1 is a multiplier. You require four multipliers together at a time. Suppose A2, B2, C2, D2 are adders, you requires four adders at a time. This is called parallel processing. In the parallel processing, all operations are done at a time with multiple resources. Okay, in the case of pipelining, suppose you have A1, B1, C1, D1. A1 can be a multiplier and that is executed at a T1 time, and A2 is a multiplier along with adder B1. I told A1 is A2, A3, A4 are all multipliers. Sorry, operations, and that can be done at a time one operation, and remaining operations also done parallelly, sorry, in a pipelining. The thing is, when A1 is doing the multiplication, it is alone for the first T1 time. But in the second time, when A2 is doing the multiplication, B1 will do the addition. B1 will do the addition and A2 will do the multiplication. Similarly, when A3 is doing the multiplication, B2 will do the addition, and suppose for an example, C1 is a shifting operation, it will do the shifting operation. All three together. Now, the number of resources are single, multipliers are only one, adder is only one, shifter is only one, and divisor is only one, like that. Not in the case of parallel processing. Parallel processing is a less inter-processor communication, complicated processor hardware is required. In the case of pipelining, more inter-processor communication is required, simpler processor hardware. I hope you understood what is pipelining and parallel processing. Let us go to the next slide. It is called FPGA. Why FPGA? Why FPGA? Before and all, when you draw electronic circuit, you have to go with page by page drawing. Page by page drawing, and you have to draw like a house layout. You have to draw with a page by page drawing, and linking one paper to another paper in the drawing is very difficult. So what they did is in FPGA, it is used by hardware description language. Hardware description languages are Verilog and VHDL. A circuit is described by a set of instructions, set of programming instructions, that is called FPGA. This described by FPGA, hardware description language. Specification of FPGA is number of LUTs, lookup tables, and logical elements. Logic array blocks, lab, placement and routing, critical path, and the price. Specifications of FPGA are how many LEs it has. That is the capacity of the FPGA. If the LEs are less, we cannot go for complex implementation. If the LEs or logical elements are more, we can go for complex higher applications which requires more LEs. FPGA circuit can be configured on the fly. On the fly means downloading on the fly to implement specific software functions with better performance than on a microprocessor. With better performance than on a microprocessor. The CAD tools generally we use is ISC Xilinx, Quartus 2 Ultra, Xilinx Ultra, Magma, Synapsys, Cadence are company names. Quartus 2 is the software supported by Ultra company. ISC is the software package platform supported by Xilinx company. Magma is one of the simulator, and Synapsys, Cadence and all back-end tools. What is front-end tool? What is back-end tools? Front-end tools are used for implementing an application using the back-end tools. Already somebody written a code for NAND gate. If you use a NAND gate, NAND and simulate, that is called front end. If you design your own NAND gate, that is called back end. Your own NAND gate with power specification, channel length, sizes and nanometer technology, like that, then it is called back end. FPGA can be reprogrammed to perform another specific function without changing the underlying hardware. Okay, FPGA can be reprogrammed to perform another specific function without changing the underlying hardware. This is one of the spot on to FPGA block diagram where the CLB's configurable logic blocks are there. All are interconnected by interconnects. DLL, digital logic clock, DLL, there at the corners, and black RAM are surrounded by the IC, and IO pins are there, IO cells are there, IO cells, input output blocks are there. It's an interface between the package pins and the internal logic. Configurable logic blocks provide the functional elements to implement most of the logic. What is inside a CLB? The inside a CLB, it is a multiplexer, flip-flop, and gate, NAND gate, like that. Okay, delay delay locked loops, DLL distribute the clock and properly compensate for delays. DLL is having the clock distribution function. Block ROMs each has 4096 bits. This is the simple structure of an FPGA where CLPs are the center core, and RAM IO cells are at the outer core, and DLL are at the corners. What is ASIC? ASIC is a application specific integrated circuit. As I told, it is a tailor-made shirt. One of the ASIC IC is OQ44434. It is a custom-built crypto chips used in FLIPS. Cryptography is used for security. Crypto Museum Ultra OQ4434 H8715 is IC, which is used for cryptographic function. It is an ASIC. It will do only encryption and decryption. It will not do any other function. That is why it is called as an ASIC. This slide shows what is an FPGA flow, what is an ASIC design flow. ASIC FPGA design flow, design specifications, HDL plus simulation. What is HDL? Hardware description language. We are using a Verilog or VHDL, and we are simulating, and that will be synthesized place and route, and you'll be dumping the code on the board on a spot on 3 code or ultra FPGA code, ultra FPGA board. But in the case of ASIC, design specifications, HDL plus simulation, synthesis, static time analysis, floor planning, place and route, static time analysis, advanced verification, verify the chip. All are done on the ASIC design flow. It will be verified, the chip will be manufactured and will be verified for the function. In the case of FPGA, FPGA is like a general purpose processor. When whatever you are writing the code, whether you can writing for a multiplier, when you dump the multiplier code on the FPGA will act like a multiplier. When you write a code for adder or as a counter, when you dump the code on the FPGA will act like a counter. Okay, but not like a ASIC. ASIC will do only one function, and if you want to do another counter, you have to design another IC. Okay, that is the main differences between the process flow between FPGA and ASIC. Comparison of SOPC, ASIC and others. Software flexibility. All three are having software flexibility. Hardware flexibility is only with SOPC, system on programmable chip. Reconfigurability. Reconfiguration is possible with SOPC, not with ASIC or fixed processor. Development time and cost is less for SOPC. One for ASIC and fixed processor, it is costlier. Peripheral equipment cost is low for SOPC and ASIC. Fixed processor, performance wise, it is good for ASIC and fixed processor. Production cost is high for SOPC. Power efficiency is low for SOPC and it is good for ASIC. What is SOC? System on a chip. The technology advances. Today chip contains 100 million transistors on a chip. Transistor gate length of and the order of nanometer. I told already in the first slide that the man is of height 1.5 meter, 1.5 meter, and the insect is having millimeter, virus is having micrometer, and the atom is nanometer, virus is having nanometer, and the atom size, silicon atom size is in 0.24 nanometer. Moore's law says that every 18 months the transistor on a chip doubles. But now the Moore's law fails. Why? Because the number of chips on a IC, if it is going on doubling, that is mean on a silicon platform, on a silicon chip, if you are increasing more number of ICs, that means that the length between the source and the drain are reduced more. You cannot do much reduction after a particular distance. If you do reduction of the length between the source and the drain, it will lead to short channel effect. Leakages and tunneling will happen. Body effect will be there. Okay, so we cannot go on further reducing the chip, and the Moore's law fails nowadays. The consequences: components connected on a PCB but integrated onto a single chip. Components are connected through a PCB but integrated on a single chip. What is SOC? The VLSI manufacturing technology advances has made possible to put millions of transistors on a single die. It enables designers to put system on a chip that move everything from the board onto the chip eventually. SOC is a high performance microprocessor since we can program and give instruction to the microprocessor to do whatever you want to do. It are all the statements initially assumed by different view in the definition for SOC. People see will tell SOC is the efforts to integrate heterogeneous, note it down, what is meant by heterogeneous, analog as well as digital. Heterogeneous or different types of silicon IPs on the same chip like memory, microprocessor, random logic and analog circuitry all together on a same chip. All of the above are particularly right but not very accurate. What is SOC? SOC not only chip but more than a more on a system. SOC is chip software integration. The SOC chip includes embedded processor, ASIC logic and analog circuitry. Embedded memory, the SOC software includes OS, compiler, simulator, firmware, driver, protocol stack integrated, development environment like debugger, linker, ICE, application interface, C, C++, and assembly. The SOC integration includes the whole system solution, manufacturer consultant, technical supporting. Applications of SOC. One of the application for your FTP is related to industrial 4 industry 4 applications: speech processing, image and video signal processing, information technologies, PC interface, computer peripheral interface, controller, DVD controller, printer, LCD monitor, USB, PCI, and IDE. Data communication, wireline communication, DSL, Ethernet, wireless communication, Bluetooth, MLAN, 2G, 3G, 4G, WiMAX, UWB, all are involving with SOC. Bluetooth is also involved with SOC and DSL, the digital subscriber loop. Ethernet is also routers or net LAN WAN are involved with SOC. Benefits of using SOC: cost, performance, power, and size are reduced in the case of SOC. Reduce the overall system cost. It increases the performance. It lowers the power consumption. Reduce the size. This is a part of a SOC. Memory is there, memory block, microprocessor design core, data and signal distribution, digital signal processor, custom user block, power distribution and management system, ADC, DAC, analog to digital converter, digital to analog converter. These all ADC, DAC itself is called mixed signal processing. You know that analog is a analog signal and that is converted into a digital signal. So ADC is an example of mixed signal processing. DAC is similar way in the example of mixed signal processing. All is available in the SOC. Okay. Clock signal distribution and control signal, audio signal, intermediate frequency signal, video signal outputs. This side, server data, power, radio frequency signal, control signal, all are under part of the blocks of SOC. OMAP is the recent topics in SOC. It is having ARM Cortex. This is used in cellular telephony, cellular mobile communication. Okay. Uses ARM Cortex A8 and 2D 3D graphics accelerator, image signal processor, shared memory controller, timers, interrupt controller, mailbox, boot secure ROM, M Shield security technology, AES, PKA secure WDT keys and things. If you look into this diagram, this shows that JTech emulation IF, GPMC, STRC, GPIO, general purpose IO, camera interface, system interface, power reset clock manager, um, MCBCSC, high speed USB to OTG controller, TSC 2046 touchscreen controller, all together is called as a single chip. All together is on a single chip. Navlink GPS, Hollywood mobile TV, Boiling MW LAN, Bluelink Bluetooth, TCS modem chipsets, battery charger, power manager, audio video codec, HS USB transceiver, keypad. All are interlinked to you on a single chip called OMAP 3430. It is one of the SOC for cellular mobile communication. Next, let us talk about why this SOC is more famous and things. SOC helps hardware software co-design. What is hardware software? Hardware is FPGA, software is C programming. This SOC helps hardware software co-design. Look at the diagram. Design entry tool. It's coming from additional user hardware. HTL or schematic, FPGA synthesis tool, process core configuration tool. Some of the applications will be played on or implemented on a FPGA, and some of the part of the applications will be written as a C programming, all together put together in a execution platform that is called hardware software co-design. Okay, FPGA tool, synthesis tool, FPGA place and route tool, program FPGA and initialize memory, all are in the hardware part. Hardware part. In the diagram, the shaded regions are hardware and the plain regions are software. Software means written in C and C++, written in C and C++, and hardware means it is implemented on a FPGA. Processor configuration data are implemented on a C programmer, and this C programming output is converted, not only C programming, HTL programming like Verilog VHDL code synthesis also can be converted into binary file, binary program, and will be embedded on a memory in the hardware. That is hardware software co-design means in general a simple word, some part of the program will be in the FPGA portion, another part of the program will be in the C portion, C programming. That is why it is called as hardware software co-design. Research areas in the hardware software code design are languages. You can find a new language for hardware software code design, architectural exploration tools, algorithms for partitioning. To algorithms for partitioning means which part should be in hardware, which part should be in software, that should be decided by an algorithm. So algorithms for partitioning, scheduling, hardware, software and interface synthesis, Verification and testing also is an interesting field in VLSI, where we can work on it to find a new algorithm for testing and verification. Hardware software interface synthesis tools are like ISE and Proteus. You can develop a platform for hardware software co-design. Verification and testing is also important. Types of course, there are different type of course are available. Main course are soft course, firm course, hard course. The three major types. Soft course are nothing but when the say for an example, when a box is there, plain box, it will act like a box, like a FPGA. Box is the FPGA. When you, as I already told, when you write a multiplier program and you dump on the code on the the FPGA will act like a multiplier. When you write a adder code and dump on the FPGA will act like a adder. But this you can write similarly multiplier and adder. You can write similarly a processor itself using a code. HDL code itself will write for a processor as a processor. Then if you dump that code on the FPGA will act like a processor, as like a multiplier. Then that processor is called as soft core processor, because it was written by program. It is not physically available. Okay. A synchronizable HDL description. A synthesizable HDL description is called a soft course. A gate level netlist that meets timing assessment is called firm core. A gate level netlist is the after synthesizing you will be getting a netlist. The gate level netlist that meets timing assessment is called a firm course. Hard course or nothing but includes layout, technology dependent time information. Your microprocessor are called, power PCs are called hard cores, and soft cores are nothing but writing instruction set and it will act like a processor or act like a processor. Okay. That is called soft cores. The next diagram will indicate Ultra is a company name producing FPGAs. Spartan is a FPGA name produced by Xilinx. The Ultra FPGA is having a soft core processor. It's called Nias 2. In the Nias 2 processor, we can have both Nias 2 processor, JTAG debug module. The Nias 2 processor is written by program. So it is called as a soft core processor. It is not physically existing like a IC chip. It is written in a HDL language as a processor and dumped on a FPGA, and it will act like a processor. That is why it's called as a software processor. The software processor is having Nias 2 processor, reset and clock inputs, JTAG debug module, JTAG UART interface, USB processor interface, host computer, Avalon switch fabric, on-chip memory, switches parallel input interface, LEDs parallel output interface. Output interface are connected to LED 0 to LED 7, and switches switch parallel input interfaces are connected to SW0 to SW7. All are called outside switches and LEDs are having interfaces with Nias 2. Nias 2 is a soft core processor. It is having ALU, addition, subtraction, shifting, and operation like that, and it is having only two input port. Two input ports are A and B. Now I told that what is meant by hardware and software design. NIAS now it is called a software because it is written by HTL codes. Now I am writing a custom logic. Custom logic means my custom shirt like that. I am writing a application program and I am connecting that custom logic to the NIAS 2 through A and B. A and B are the interface input interfaces, and it is custom logic. The custom logic can be written in the hardware. The custom logic can be in the hardware, the first in first out memory or other logic. Okay, hardware, and NIAS is a software. So the custom logic and NIAS is connected like this. A and B are the inputs and one output. I did my PhD work on in 2009 itself with the NIAS 2 processor. Any pattern recognition will have a block diagram like this: input, speech, feature extraction, training, recognition, like that. The trained models are used for recognition, input, speech, or feature extraction, and the feature extracted input speech is given to the training, and the trained models are used for recognition. Okay, one of the feature extraction techniques in speech is LPC coefficients. The LPC coefficients are obtained from pre-emphasis LPC, linear spectral coefficients. Okay, subtle analysis. The sampled speech is passed on to the pre-emphasis, and the pre-emphasis are nothing but filtering, and after filtering your after filtering the frame is formed, and the windowing is done. Frame nothing but number of samples as a group. Windowing is multiplying that windowing with triangular window or rectangular window, like that. Autocorrelation and LPC septal analysis. After forming this septal coefficients, code books are formed, and code books are formed with things with K means algorithm. And find the index of the nearest code book vector for each frame, and train the HMM for each digit for each user, and average the parameters. Trained models for each digit is trained by trained models. All these are given to the HM recognition. Hidden Markov model. In my thesis I used hidden Markov model and artificial neural network, and hidden Markov model is used for use better performance than artificial neural network. Why I am talking this topic is I told about hardware software design. I did this application of speech recognition using the hardware software design on the SOC. That is why I am giving this example. Find the index of the nearest code book vector for each frame, and then find the output probability using Viterbi algorithm for each model. Find the model with the maximum probability as the uttered digit. Okay. Look at this model of HMM. Since I used only 10 digits, 0 to 9, I have 10 models. The observation is probability, finding the nearest codebook action, and it is given to the HMM model. The HMM model will be of n comma a b pi matrices, and this NAB pi matrices will give probability of the observed digit is whether it is 1 or 0 or 9, and the scoring of that probability will be selected by based on which probability of the digits are maximum. Okay, this is done with C program, and the other part is Viterbi decoding is done with Verilog coding. So I combined this hardware and software co-design in the NIAS2 processor. Ultra Cyclone 2 FPGA is used for this hardware software co-design. Now advanced boards are came for implementation. During 2009, I used Ultra Cyclone 2 FPGA board. Now the famous tool for FPGA from Xilinx is Zinc ZYNQ. A Zinc 7000 is a rich dual core ARM Cortex used for cellular mobile communication. A9 processing system, 28 nanometer technology. I told what is the recent research work. The recent research work is on 7 nanometer technology, but this zinc board is on 28 nanometer technology, Xilinx programmable logic in a single device. The ARM Cortex A9 include on-chip memory, external memory, interfaces, and a rich set of peripheral connectivity interfaces. Okay. Neon ARM Cortex includes timer counters, general interrupt controller, DMA, configuration, AMBA switches, SBI, I2C, CAN, UART, GPIO, SDIO, USB, like this. The SOC design requirements are price, performance, and power, system support and portability, IP reuse, architectural reuse, open industry standards, standardization around data management and IP, testability, process dependency, design methodology, partition based on functionality, partition based on hardware and software components, modeling, consistency and accuracy at different levels, continuum from a virtual prototype model to simulation, emulation, and rapid prototyping. Models used by software developers should be directly tied to implementation. Simulators are only as good as the models. Robustness of tools are also requirement for SOC. Challenges in SOC are complexity. Silicon complexity is the main thing in challenges. Impact of process scaling and new materials and architectures, previously ignorable phenomena now have impact. System complexity, deep submicron effects, crosstalk electron migration. I told that when you go on reducing the channel length, the distance between the source and the drain, you'll be having deep submicron effects. Crosstalk electron migration, wire delays, mass cost, power management, system level integration of heterogeneous technologies, development of SOC test methodology verification. The topic of today FDP is mixed signal chip. What is mixed signal chip? Mixed signal chip is a perform some whole function or subfunction in a larger assembly, such as the radio subsystem of a cell phone or the read data path and laser sled control logic of a DVD player. They often contain an entire system on a chip. Already I told what is a system on a chip. So mixed signal chips also system on a chip with analog and digital signal together on a chip. Examples of mixed signal integrated circuits include data converters using delta sigma modulation, ADC, DAC, analog to digital, digital to analog using error detection and correction, digital radio chips, digitally controlled sound chips are also mixed signal circuits. With the advent of cellular technology, network technology, this category now includes cellular telephone, software radio, LAN and WAN router integrated circuits. What is Industry 4? Industry 4 speaks about intelligent networking of machines and processes of for industry with the help of information and communication technology. So This industry 4 involves industry 4 involves uh, development of automation and things. Intelligent refers to the intelligent networking of machines. Automation, the automation requires analog and digital signals together. So mixed signal chips are useful for industry 4 with IoT. This is the application of mixed signal processing. One of the mixed signal processing example is SOC. Industry, this is my last slide. Industry 4 is often used interchangeably with the notion of the fourth industrial revolution. It is characterized by, among others, even more automation than in the third industrial revolution. The bridging of physical and digital world through cyber physical system enabled by industrial IoT, a shift from a central industrial control system to one where smart products define the production systems, closed loop data models and control systems, and personalization and customization of products. The goal is to enable autonomous decision making process, monitor assets and process in real time, and enable equal real time connector value creation networks through early involvement of stakeholders and vertical and horizontal integration. What is an industry 4? Industry 4 requires cyber security, augmented reality, big data, autonomous robots, additive manufacturing, simulation, system integration. The system integration involves mixed signal processing, cloud computing, Internet of Things. All together is required for Industry 4 revolution. Most Industry 4 initiatives are early stage projects with a limited scope. The majority of digitization and digitalization efforts in reality happen in the context of third and even second industrial revolution technologies goals. We are coming to the end of the session. Uh, SOC design challenge, IP quality verification, all are deep submicron effects, all are coming under SOC. System IP completeness, system partitioning, IP reuse, power management, time to market. So today I started with the topic of why we need initially implementation tools. The implementation tools are microprocessor, DSP process, and I told that signal processing operation is better for DSP processor, and I told what is SOC. I gave one example of speech recognition using SOC, and what is mixed signal processing and what is industry 4 revolution. With this, I'm concluding my talk. Any questions, please? Bhaskar?
Yes, ma'am. Dear
I'm
participants, if you have any doubts or queries, you can ask now. You can either post your question in chat box or else you can unmute yourself and ask the resource person.
any questions, Pa? Mr. Bhaskar, any questions in the chat box?
No, ma'am. There is no question from participants yet, ma'am.
Okay. This is the end of the session, but there is no end to technology. I thank Konganadu College of Engineering for inviting me to give the session, and especially Mr. Dinesh Kumar. And I'm happy to be presenting my talk with the Konganadu College of Engineering. And since they are in the remote place in my native place, they are conducting many more events, and they are having their own customized principles to have students discipline and placements, and I wish them all the best. For the students also, Bhaskar and his friends, to have a good placement record. Thank you.
Thank you, ma'am. Ma'am, let me conclude the session, ma'am.
Yeah, yeah.
The roots of all goodness lie in the soil of appreciation. In this way, I would like to thank our today's resource person, Dr. V. Amuda, Professor, Savita University, for providing the wonderful session on the SOC design. Thank you so much, ma'am, on behalf of organizing team.
Thank you, Pa. Thank you.
Thank you, ma'am. Ma'am, you can leave, ma'am. Dear participants, the day 3 session 1 attendance and feedback link is posted in chat box. It will be open up to 30 minutes only. So kindly fill it soon. Thank you all. Dear participants, the day 3 session 1 attendance and the feedback link is posted in chat box. It will be open up to 30 minutes only, so kindly fill it soon. While filling the feedback form, kindly choose your respective FTP ID. Thank you all.